Hello and welcome back to the Hyperthesis episode 23. Today we're going to be talking about some very interesting part that I personally don't know much about, which is the atmospheric science or atmospheric physics. And my name is Billy.
I'm Patrick.
And I'm Liam.
Alright, before we start, is there any news or some exciting things that happened in the past week or something you learned?
So I'm I'm taking the intro topic today, and I'm using it to start off our discussion on our main topic because there's so much stuff I want to talk about that I need this time, you know. But it is interesting because I did look into it a bit more than I have in the past. Why is the sky blue? And we have talked about this a little bit in the past. So, but I wanted to go through it in more detail because today's main topic is on atmospheric optics, specifically. Just how, roughly put, it's the study of optical characteristics of the atmosphere or optical phenomena which occur within the atmosphere. So, in this episode, I'm going to be talking a lot about how the sun makes things like rainbows appear and why. I'm starting with the most obvious one. Why is the sky blue? A warning: if you're going to look for these things, don't stare at the sun. Protect your eyes. You don't want to blind yourself. And additionally, I want to get through a whole bunch of things, but there's not enough time. So the stuff I'll talk about today is probably a quarter of the things I wanted to talk about. So one day we'll put out some other episode talking about other atmospheric optical phenomena. But for now, I'll just start with kind of the most obvious and common ones. So why is the sky blue? To start, the atmosphere is made out of some gas and it surrounds the Earth. And this gas consists of many different molecules, and it contains things like nitrogen, carbon, hydrogen, and of course oxygen. I'm not sure if you guys know roughly like what percentages the composition is. I don't really know off the top of my head. I know there's a lot of nitrogen.
The atmosphere is about 78% nitrogen, 21% oxygen, and then the remaining 1% is all the other gases, including carbon dioxide. Now, I think carbon dioxide currently is just over 400 some parts per million. As for the other ones, they are very, very minute in their composition.
Mm-hmm. So, yeah, there's these air molecules, essentially. And what happens is that light from the sun, white light, which consists of every other color of the visible spectrum combined, Roy G. Biv is what I call it: red, orange, yellow, green, blue, indigo, violet. I'll probably say Roy G. Biv again, so that's just the definition. Out of all those colors, red has the largest wavelength of about 750 nanometers, and violet has the shortest, around 400 nanometers. And of course, the sun emits other forms of non-visible light, like UV light, ultraviolet, which has an even smaller wavelength than visible light, but we'll focus on visible for now. So as this white light enters the Earth's atmosphere, these air molecules will scatter tiny proportion of this light in every direction.
Well, all this sounds a little too technical. I feel like wavelengths is not really, a lot of people are not familiar with wavelengths. I think it's easier for us to talk in terms of frequency because it makes sense, people use it all the time, right? So red has lower frequency, so lower energy, and blue or violet has higher frequency, so more energy, right? It's more dense. I mean, you go up or down faster. You think of harmonic oscillations, right?
Yeah.
I think it's just wavelengths a lot of people are not familiar with, even like science students.
No, the physicists love wavelength. Well, I only ever talk about wavelength because it's like a physical thing. Frequency is a physical thing, but I don't know. I like wavelength better. I'm going to talk about wavelength. But it's, large wavelength, same thing as small frequency. Large frequency is the same thing as a small wavelength. So anyway, turns out the blue component of this white light scatters a lot more than all the other colors. So all the light enters the atmosphere, and blue scatters the most, which is why you see so if you're on the ground looking up at the sky, it's why you see blue light, because more of the blue light scattered down to you, where the rest has not. And the sky's not pure blue; it also scatters other colors, but it scatters blue light a lot more than the other colors. Red being the weakest, since it has this larger wavelength or smaller frequency. Why does it do this? In our universe, things tend to interact with each other when they're around the same size. So I have this kind of analogy I came up with, where if you imagine a bottle floating in the ocean, and this bottle has two materials in it, which if the bottle's shaken, they'll mix together. If this bottle's hit by some ocean waves, say they're like a meter tall, depending on the size of the wavelength, depending how long these waves are, they'll cause the bottle to mix more violently or less violently. So if you have a meter tall waves, which are only very short in wavelength, so there are these kind of sudden waves that just smash into the bottle. The bottle's gonna oscillate up and down very, very fast, and it's gonna shake a lot, and the stuff within it's gonna mix. But if the wavelength of these waves is very, very long, the bottle will more so slowly bob up and down, and it won't be violently shaken. So these waves that are smaller, closer to the sides of the bottle, cause it to shake more and the things mix. So they interact with it more than the long wavelengths do.
Well, then it's kind of strange to say that. Then, well, does amplitude matter how tall the wave is? If you think of your analogy, your mechanical wave, you have a 10 meters tall wave, but a really long wavelength. Like, it's still gonna shake the bottles.
Not really. If you have these massive waves, it doesn't really matter how tall they are. I mean, technically, I guess it does, but like 10 meters tall, if the wavelength is very long, the bottle's still going to slowly rise to the peak of it, and then slowly rise back or sink back down.
The tsunami was beg to differ, but
Well,
sure.
Tsunamis are actually very low amplitude and very long wavelength in the ocean, I believe. And what happens is that as they approach the shore, the wavelength becomes much smaller and the amplitude increases a bunch. So in the middle of the ocean, if you get hit with a tsunami, you'll barely notice it. You'll just kind of bob up a bit and down a bit. And then it's when it hits the shores, it becomes massive.
Yeah, it's the compression because it gets shallower. I think we did some calculation on that in school.
Yeah,
I think. Right?
I don't know if I've ever done it, but I've read about it before. But the idea is that the air molecules in the sky, they're about 1,000 times smaller than the wavelength of visible light, or you can say they oscillate at a very much larger frequency than the frequency of light. So the light that goes through our atmosphere doesn't interact with it very much, but because there's so much gas in our atmosphere and so much light coming in, a decent amount of it does interact with one another, even if they're nowhere near the same size. And because blue is a much smaller wavelength, much more of it interacts with these air molecules than the red light or the higher colors of light. With this knowledge, actually, we did this calculation, didn't we, in our undergraduate electromagnetism class? We calculated the dependence of wavelength or frequency of how light gets scattered in the atmosphere. It's a phenomenon known as Rayleigh scattering.
Yeah, that really scattering what we did. And also, what I think you haven't mentioned yet, probably will soon, because sky is not just blue, right? It's orange when it's evening or dawn, right? So there's what's called angular dependency that comes with Rayleigh scattering. You want to talk a little bit about that?
Well, the reason why the sky gets red at sunset, it's actually it's because the light has to travel through more atmosphere than it does during the day. So if you look straight up, there's not near as much atmosphere between you and space as there is if you look down the horizon. So as the sun's setting, all of the light that gets scattered more than red light, so blue, indigo, green, whatever, all those colors scatter more than red. They scatter away through the atmosphere faster. So the light traveling from the horizon during a sunset, all the other colors have been kind of filtered out by the time it hits you, and you're left with red light. So this might make you ask the question, well, the visible spectrum, violet has the lowest wavelength, not blue. So why is the sky not, a purpley violet color? And there's two reasons for this. The first reason is that the spectrum of emitted light from the sun, it's weaker in the violet than it is the blue. So out of all the light that gets scattered in the atmosphere, it's there's less violet essentially. And the second reason is that human eyes are bad at picking up violet light compared to blue. So if human eyes were built or designed differently, or if we evolved differently, the sky could very well be more purpley color than it is now, which would be kind of neat, I think.
Yeah, well, the eye was originally developed to look underwater, right? Right. We were aquatic creatures, so there was really no reason to look at the sky because we were underwater. But now that we are on the surface, it's just what it is. I mean, there's blue, there's violet, and I think your point about what's come out of the sun is good too, because you would think, right? It's so hot, it radiates just white lights, and every frequency should have the same thing, but it's not, right? There are characteristics that depends on what's the elements that make up the sun and the corona and all these stuff. There are different composition that give out different spectrum of light.
Yeah, it's related to black body spectrum. Although the sun is definitely not a perfect black body, you can approximate it as one. So it's got that. If you just Google black body curve, it's got like a kind of emission spectrum that looks something like that. But yeah, so that's kind of the most obvious atmospheric optical phenomena is why the sky is blue. Unless you live maybe in England, you definitely see a blue sky a lot. So that's kind of obvious. And for our main topic today, I want to talk about other types of atmospheric optical phenomena. I'm not sure if you guys had anything you specifically want to talk about, but I wrote this massive list because I've recently become kind of obsessed with this stuff. Like rainbows. Rainbows are related to my research a little bit through these branches of mathematics called asymptotic analysis and catastrophe theory. I'm not going to get into that. I think I've definitely mentioned this before and talked about rainbows, but the primary optical phenomena I want to talk about are rainbows, diffraction phenomena like coronas, ice halos, and the northern lights. But I think someone else will talk about the northern lights later.
Well, when you say rainbows, you mean like atmospheric rainbow, or you just mean there's 7 colors in general? Because I can pick up a prism, and if I tell a kid, "What's this?" They would say rainbow, right? So I mean, is rainbow and prism the same? I mean, that's clearly a diffraction rainbow, right? Would you call that a rainbow, or is there? How do you, for you, define rainbow?
Yeah, I guess it depends on the context because, I mean, technically a rainbow is a bow made through the rain, but I think historically people saw rainbows in the sky, and then Newton did his prism experiment, and the visible spectrum was split up into the colors of the rainbow. So when you say rainbow, you generally just mean the colors of the rainbow. But in this episode, when I say rainbow, I guess I will mean, if I say rainbow, I mean like specifically a rainbow you see in the sky, and I'll try and say colors of the rainbow if I mean something that's not a rainbow. Although there is some context. They kind of go back. They kind of are used interchangeably. It's one of those silly physics things where context matters a lot, and you kind of need to know what you're talking about, or you need to be careful. So I'll try and be careful. So all these phenomena occur in different layers of the atmosphere due to light interacting with gas, water droplets, dust-like particles, or ice crystals. A lot of them can be seen almost every day if you know where to look. And some of them, which I probably won't talk about today, are so rare that you might see them once in a lifetime. And that's with knowing where to look and actively trying to find them. So to start, one other issue is that I'm talking about all these really cool looking optical phenomena that look like the colors of the rainbow. It's hard to do that over a podcast. So I highly recommend that as I say these things, you Google them or write them down, Google them later. And additionally, on our Instagram page, I'm going to be posting photos of everything I talk about today, so you can go look there. And I'm getting most of my information from this website called atoptics.co.uk. So it's an atmospheric optics website which talks about a lot of this stuff.
Well, I have actually a more important colloquial question for you. That's because you study rainbows, and I think a lot of people would be interested in this. What happened at the end of rainbow? Is there a leprechaun with a gold pot, or is there an end to that rainbow? Right? Because when you see the rainbow, it curves down onto the ground. But is that as a real? Is it touch the ground, or are they really just it's like an illusion that it goes through the ground? I don't really know. I actually never looked into it. Maybe you have an answer.
Yeah, so let me just talk about how rainbows are formed and what they are. And if I don't remember to come back to that question, ask it again. I'll try and remember. So rainbows, yeah. So let's talk about a typical rainbow. So like if you look up in the sky, a single arching rainbow, nothing fancy like a double rainbow yet. Rainbows can form when it's raining and the sky is not completely covered in clouds, so the sun can be seen. So the sunlight being kind of visible is important because you need sunlight to create the rainbow. You need bright sunlight, not just sunlight coming through clouds. So imagine this white light from the sun, and this is light that has been scattered in the atmosphere already, so it's gone through and relatively untouched, and it enters a single falling raindrop. So imagine this raindrop as a physicist does. Imagine this raindrop is a sphere. Raindrops are not spheres, but we can say approximate that for now. What happens is that the white light enters the raindrop and it refracts. So it will be split into its constituent colors of the rainbow, this Roy G. Biv colors I've talked about. And since different colors of different wavelengths or frequencies of light, they refract differently. So they'll change their trajectories by different angles as they swap between mediums. So that's why as this white light enters the raindrop, it kind of gets diffused or dispersed into its different constituent colors. So what happens is that it gets dispersed, and all these colors hit the back of the raindrop, and they internally reflect kind of back towards the front of it. And then once they hit the front of it, they refract again and exit. So they refract a second time, which spreads out the colors even more, and then they exit the raindrop. Except kind of angled down towards the ground now, which is why you can see a rainbow, it turns out. So the end effect is that these different colors are separated a bunch, and it's like you said, it's similar to how white light enters a prism, and then it's kind of they're dispersed into their constituent colors. So all these different, you can imagine this light hitting our raindrop at different points, and different rays of light entering the raindrop will emerge at different angles, and the different colors will have their own angles. It turns out the strongest angle is about 42.5 degrees from its original path. And this is specifically for the red part of the light, which is dispersed. And because raindrops are not just a two-dimensional circle, they're, again, in our approximation, they're round, they're a sphere. What ends up happening is that you get this kind of cone that goes around the center axis at about 42.5 degrees, where this light will come from, and it will hit a variety of spots on the ground, but some of it goes up in the air as well. So this is pretty hard to describe, I find, over a podcast. So I definitely recommend you look at this on this AdOptics website that I mentioned before, and they have kind of diagrams that show this pretty well. But anyway, since there's lots of rain, and the sunlight is hitting many different raindrops, not just a single one. Each raindrop refracts and internally reflects this incoming white light and focuses it at about 42.5 degrees in this cone shape. So to someone on the ground, what they end up seeing is they see kind of the combined effect from all these raindrops refracting and reflecting light, and they see this giant bow of this separated, dispersed color, and that's a rainbow. The colors from top to bottom go as the spectrum of light, Roy G. Biv, so red, orange, yellow, green, blue, indigo, violet. And it like you alluded to earlier, a rainbow is it's an illusion in a sense. You're not actually seeing light coming from the sky. You're seeing light being reflected from the raindrops. So if you're standing somewhere and you see a rainbow, someone else standing somewhere else will see a completely different rainbow at all. They might see a different, they might see it at a different height. They might see not the whole arch. They might see like a part of the bow, stuff like that. They might see broader or less broad bands depending on the raindrops being hit. So at the bottom of a rainbow, it doesn't it shouldn't touch the ground because at least not to you, but if you were up higher, you might see the rainbow coming from the ground because it all depends on where the light's coming from, the angles it comes out of the raindrop.
Yeah, about all the angles, too, people think it's just diffraction, but what really create a rainbow? If diffraction didn't happen with just monochromatic, which is one color, right? Light is diffract. But what really make rainbow like multicolor is the dispersion, right?
Mm-hmm.
The dispersion relation, because the index of refraction of a material changes with the wavelength or the frequency of the light. So you can see that the violet would disperse or like diffract more than red. So that's what we call in physics the dispersion relation, because the dispersion that depends on the frequency of light.
Mm-hmm. And yeah, so diffraction is typically something that it's a wave phenomenon. And the primary bow of a rainbow you can completely describe with ray optics. Even the secondary bow, a double rainbow, you can describe with ray optics. You don't really need diffraction. You just need this dispersion that happens inside of the raindrop. So the next logical question: what does a double rainbow come from? How does that form? Because sometimes above the primary bow, you get this dark region, and then you get a secondary kind of dimmer rainbow above it. Double rainbow all the way and whatnot. So it turns out that inside of the raindrop, all this refraction and reflection that occurs, the light that leaves the raindrop and creates the primary bow, it's not a perfect process. Nothing absorbs perfectly and nothing reflects perfectly, or nothing transmits perfectly and nothing reflects perfectly. So some component of the light, instead of leaving the raindrop to create the primary bow, some of it is actually internally reflected a second time back into the raindrop. And this is what causes the double rainbow, is that this secondary reflection that occurs within it. So we call a primary bow a first order rainbow, a secondary bow, so the double rainbow, a secondary rainbow. And there's actually higher orders of rainbows. So a third order rainbow is due to 3 reflections inside a raindrop. There's a fourth order, a fifth order, a sixth order, but they progressively get dimmer and dimmer and dimmer and harder to see and more broad because of more dispersion. So reliably, you're ever only going to see a first and second order rainbow. The first time a third order rainbow was ever photographed was 2011. And it's kind of very difficult to do. And even the higher order ones we've seen now, but you have to use these special lenses and you have to have the perfect conditions. So they're quite hard to see.
I think you should briefly say what order is, because maybe people are not familiar with calculus, or even like what is order. Well, when you think of polynomials, we have order. Like in this context, what do you mean by order?
Well, in this context, I mean order corresponds to how many internal reflections you have within the raindrop. So a first order rainbow, which is your usual standard rainbow, that has 1 internal reflection, whereas a second order rainbow will have 2 internal reflections before the light leaves the raindrop, and so on.
Just to point out that most of the physics theory in physics, we only do to first order or second order. That is like, you get to reflect once or twice. And if you look at computer graphics, when you do ray tracing, you do first or second order. If you do more, it's just too much.
And there's a reason for that. It's because usually you only need your first or second order to accurately describe the theory, and the other orders will make it slightly better, but they just make it more complicated than it needs to be. And you'll be even lucky to go past first order. I mean, I personally usually do a 0th order thing most of the time. And there is a 0th order rainbow. It's definitely not typical. So a 0th order rainbow is what happens when the light enters the raindrop and just refracts. There's no internal reflection, so it just exits the other side. So because of this, there's not really enough dispersion to separate all the colors into your visible spectrum. And what ends up happening is that you get just this glowing effect. So I should mention that not every rainbow occurs opposite the sun. So the first and second order, so your single and double rainbows, they occur opposite to the sun because the light has to reflect back through the raindrop out of them. But higher order rainbows can occur in front of the sun. So what happens is that the light will bounce around inside of the raindrop, and it'll exit the raindrop going in roughly the same direction that it entered. A zeroth order rainbow does the same thing. The light just kind of goes like straight through the raindrop, basically, and it causes this glowing effect. So if it's like if the sun is setting and the sun's orangish, the whole sky will become very orange if there's raindrops between you and the sun, because it's a zeroth order rainbow effect. I've never really, I mean, I might have seen it without realizing it, but I only learned about it recently, so I don't quite fully understand it, I think, but I have a rough idea of what it is.
So, a quick question. For the zeroth order effect, can this only happen in spherical, transparent objects? Or are we talking like, I'm picturing Pink Floyd's Dark Side of the Moon album, where you have the white light going through a prism and splitting into the rainbow. Would that be considered a zeroth order?
Yeah, that's kind of what it is, except for a zeroth order rainbow in nature, you don't really get that dispersion. You don't get that light splitting up for whatever reason. Probably because the raindrops are so small, there's not enough kind of space between the light entering and leaving for the angle between the colors to be significant. But it's kind of like that. It's kind of like shooting light into a prism, except it's a sphere. I mean, raindrops aren't perfect spheres again, but I think that's roughly what it is. And because raindrops aren't perfect spheres, um, rainbows are not perfect. Although, every time we see them, they look about the same. But the size of the raindrop, it's kind of how warped it is. It'll cause like the rainbows to be broadened or thinner. It'll cause colors to be more intense or less intense. And there's a whole bunch of types of rainbows.
Just to mention, before moving on to other types of rainbows, is the fact that the appearance of the rainbow also depends on your height. Because if you've ever seen rainbows from a plane, they're circular. So they aren't actually bows, they're rain circles, I guess, or they're color circles. So the rainbows come from the fact that there's some sort of ground interacting with it. So when you see that nice arch, there's actually should be a full circle that you're observing, but you just aren't high enough. So if you've ever seen pictures, or if you've been in an airplane cockpit and you see a circle rainbow, that's, I guess, the full rainbow.
Yes, so and that's due to the spherical symmetry, like the fact that these rays are emitted at this angle, but they're like a cone shape around kind of the axis, the center axis that's parallel to the light entering the raindrop. So the ground stops you from seeing the second half of the rainbow, which would kind of go down under the ground if there was rain down there. There's nothing stopping it. So yeah, in a plane you can look down and see a complete circle, although I think it's kind of rare, but it's definitely something that can happen. One of my favorite types of rainbows is known as a supernumerary rainbow, which I think I've talked about before. But essentially, what happens is that for very small raindrops, say sometime like around 0.7 millimeters, wave interference effects start to kind of become more predominant. And these raindrops have to be very close to the same size. If they're different in size, the interference effects will kind of smear away. But what ends up happening is that smaller, kind of dimmer versions of the primary rainbow can form below it. So you'll see like this kind of concentric pattern of the primary rainbow, and then beneath it, these smaller ones appearing, which are thinner and thinner as they go. And I've only seen a couple supernumerary rainbows, and they only had like one or two supernumerary bands underneath them. But I'm very interested in those because waves and interference and whatnot. And I think they're very cool. And one more type of rainbow, I want to talk about all the other types, but again, no time. So, are called fog or cloud bows. So they're physically the same as a rainbow in the sense that, light enter, it refracts and reflects back out, except they're created by fog or kind of these particles, these water particles floating in clouds. So these particles are very, very small, these water droplets which are suspended in the air. They're usually less than 100 micrometers, which is why, fog and clouds kind of float instead of just falling to the ground like rain does. And they're my favorite because these raindrops are so small that the dispersive effects are huge. So you get these very broad bows, and because the colors which are dispersed overlap so much, they appear mostly white. So imagine like a rainbow, except it's just white. There's no like colors in it. It's not as fun as a rainbow, but it's very interesting to see, and I've actually seen 2 of them so far.
Well, I remember there's a other way to create rainbows with a sprinkler, right?
Hmm.
If you have, as a son, you go out to the yard with your children or whatnot, and you're like, hey, if you tune out the how fine the droplets just right? You just shoot it in the air and create rainbow, and it's really fun. You feel like you do something nice.
Yes, there's many different types of rainbows I want to talk about. You can make your own. Again, if you understand the basic physics, you can spray water a certain direction relative to the sun and see them. And now that I know where to look, I see them like I see a rainbow or a related phenomena like once a week. It's great. So there's all these other kinds of rainbows. I'm not going to get into them, but there are things that look like rainbows that are technically not rainbows. And I mean, I don't really care if people call them rainbows, but in these atmospheric optics groups that exist in the world, they get very offended when you things that aren't rainbows. So I'm gonna say that they're not rainbows. They look like rainbows, they involve water droplets usually, but they're technically not rainbows. And the ones I'm gonna talk about are related to kind of this fog bow or this cloud bow I talked about, where they involve these very tiny, less than 100 micrometer water droplets. So diffraction and wave interference effects are their cause. They're not like a typical rainbow, which you can describe mostly using ray optics. You need wave kind of interference effects to describe these. And the first one's called a corona. So corona, you can see it when thin clouds partially veil the sun or the moon, and the moon is typically the more common one because staring at the sun is painful. So most people don't usually look up at the sun. And the corona is this kind of intensely bright central circle which surrounds the sun or moon. Um, and it's kind of fringed with yellow and red along its edges. But sometimes what you'll see is the more impressive coronas. They also have these concentric, kind of rainbow looking rings around them, which are successively get fainter as you go away from the source of the light, so the moon or the sun. The first ring's bluish, and as you move out, you go through all the colors of the visible spectrum, where red is the outermost, and then sometimes the rings repeat, and you get that again. And these rings are a lot fainter than rainbows since they're due to diffraction effects instead of focusing events like in a raindrop. And like a raindrop, or sorry, like a rainbow, the size and shape of the raindrop can affect how big these corona are. Typically, they're like 15 degrees wide. So if you draw a line from one edge to the other, from you to one edge to the other, you'll get like a 15-degree angle there typically. And how are they formed? They're formed due kind of like the double slit experiment. So if you've ever heard of the double slit experiment in quantum mechanics, you basically have a plane wave, it hits a barrier with 2 slits, and then you get spherical waves coming out of those 2 slits, and they interfere and create a diffraction pattern. Something similar happens with these very, very tiny droplets of water. Because they're so close to the size of the wavelengths of these light that hits them, the light diffracts and creates spherical waves along the edge of these droplets, and the waves that come out of that, the spherical waves, interfere and create an interference pattern. And the end result is, once you combine the effects from all the different water droplets, you get a corona in front of the moon or the sun or any other bright light source. There's also other effects. Since these are water droplets, the light can also, instead of just diffracting on the edge of the drops, it can enter the water like it does in a rainbow, and it creates all these other kind of effects. But they're so small compared to the diffraction effects that you can ignore them. So this means that you can create corona with things that aren't water droplets. You can create them with like dust or pollen, or you can see them with all kinds of other things, even little ice crystals. They don't have to be spherical, and they don't have to be transparent. So you can see corona if it's that time of year where there's lots of pollen or in front of the sun. You can sometimes see them, which I think is kind of neat.
I will say in Alberta, we get to see them a lot because of forest fires during the summer.
Oh,
so there's a
really?
lot of smoke particulates in the air.
That's interesting. So the smoke, yeah, the little smoke particles, probably like carbon or coal or whatever bits in front of the sun cause that, or the moon. Oh, there's one phenomenon called a glory that I want to talk about, but maybe I should get straight to ice halos. I don't know. I'm going to talk about it. The glory, a majestically named phenomenon that looks like a corona, except it doesn't have this very bright region in the center of it, and it appears as as circular rings that have the visible or that have the kind of colors of the rainbow. And it always appears directly opposite of the sun, so at the anti-solar point. So if you're standing and the sun's setting, your shadow will kind of get longer and longer, and the point that that shadow tends to is the anti-solar point. It's just the opposite of the sun. So glories are really neat because they're formed when light is scattered backwards by individual water droplets. So you might think, hold on a minute, like, isn't that what a rainbow does? Yes, but no. So what a glory does is that the light enters the raindrop, but it gets scattered exactly back in the exact same direction it came from. It doesn't deviate at all. If it comes in at 0 degrees, it does a 360-degree turn and scatters. And you cannot describe that with ray optics, and you can't actually even describe that with your typical kind of wave optics. You need to take into account surface waves. So what ends up happening is that the light, it enters the edge of this small water droplet, and it travels as a surface wave for a little bit, and then it internally reflects. It hits the back end of the water droplet. It travels as a surface wave again a little bit, and then internally reflects back towards the direction it came from. And then it travels as a surface wave a little bit more, and then it exits in the exact same direction it came from. So that's why these kind of concentric rainbow rings will appear at the anti-solar point, exactly opposite of the sun. So because of this, you can often see them in planes. So if you're in a plane and there's clouds underneath you, you can look down at the clouds, and if the sun's above the plane, you'll often see surrounding the plane's shadow kind of this rainbowy looking ring, or like a concentric circle of them. And I saw that for the first time coming back from the UK the other day. Well, the other day, a few months ago, but it's the only reason why I know they exist. I was like, oh, that's not a rainbow. What is it? So I think those are very cool because it's an example in nature of where surface waves are important. And surface waves are kind of a big topic in certain branches of physics. Finally, my last thing I want to talk about are ice halos. So these are different than rainbows and these wave diffraction phenomena. They're a class of atmospheric optical phenomena, and they occur up in the atmosphere. So they're not like rain, or they occur in clouds. So typically, what happens is that tiny ice crystals in the atmosphere can create halos due to refracting and reflection of light. So similar to how raindrops do it, now just with ice crystals in clouds. And typically they're in cirrus clouds, I think they're called. These kind of wispy, wavy clouds as they go between the Earth and the sun. So what's cool about that is that, like a rainbow, you can look at a rainbow and you can kind of look at these macroscopic properties and determine what's going on with the raindrops. You can look at ice halos and determine like what kind of crystals are in those clouds and how big they are and so on. So halos can be seen all year round from the tropic to the poles, and they occur way more often than rainbows do. The clouds that they form in the cirrus clouds, they're quite high, like 5 to 10 kilometers in the sky. So they're always cold regardless of their location, which is why, you could be in Hawaii or something and see one in the sky. You could see ice crystals up in the atmosphere. And the most common type, it's called a 22-degree halo. So it's this large ring, and again, it looks like a rainbow, but it's not technically a rainbow. It just has these Roy G. Biv colors. And it surrounds the sun. So from inside to outside, it starts as red and fades to blue, and they can be pretty faint. And the name comes from the fact that if you draw a straight line from yourself to the sun, and then another one from yourself to the edge of the halo, there's a 22-degree angle. And these form due to the refracting of light through hexagonal column-shaped ice crystals. And most of them are formed by large imperfect columns or clusters, but the finest and kind of most vibrant of these 22-degree halos, we don't actually know exactly how they form. We know they have to be kind of formed from these ice crystals in some way. But their orientation matters and their exact shape matters. So for very vibrant 22-degree halos, we don't actually understand how they work perfectly. So which is interesting because 22-degree halos are by far the most common. I've seen 3 of them in the last 3 weeks because I know where to look and I know when to look. They happen all the time. So the most common is the least understood, which I think is interesting.
Yeah, I think like that's a pretty common thing to have. Like when I study water, water is very common. It's one of the least understood material too.
Yeah, water is the miracle molecule, isn't it? So it all these ice crystals in the atmosphere, again, like they probably wouldn't be. I don't know this at all. Correct me if you know I'm wrong, but I imagine water has a big part to play in their geometric structure. Like snowflakes, when they form, they're all hexagonal. They have this kind of 6-fold hexagonal symmetry, which you can talk about in kind of solid state physics and crystal structure. But because it all comes down to the special properties of water, and because it's this polarized molecule. So I imagine all these optical phenomenon, these ice halos, they all form because of this special symmetry that you get from the water molecule.
So, an interesting thing about this, and I see it might be the next section, but there are different forms of ice. Feely might be able to expand on this more since he worked a bit with water. But ice doesn't necessarily have to take on a hexagonal structure. So, like snowflakes are 6-sided. Ice can also take on a cubic structure. So, if you think about just like a little cube, that's what the water molecules can look like under certain conditions when they freeze. Now, this type of cubic structure is what's responsible for what are known as sundogs in the atmosphere. So if you've ever seen sundogs, they occur when the sun is quite low, and it almost looks like there's 2 pillars of light on either side of the sun, and you might get something on top, but it almost looks like there's kind of multiple different suns in the sky. And these are not caused by hexagonal ice, as was previously thought, but a student who we've worked with actually did research on this and looked into cubic ice, and apparently sundogs are formed from cubic ice in the atmosphere. So you need quite cold conditions. I think it happens around -40 or colder, so it's a bit more common in colder places or in the high atmosphere. But it's this cubic ice that causes sundogs, not the regular hexagonal ice that we're used to.
Okay, that's very interesting because my whole rant I have here is about how they're formed from flat plate-like hexagonal ice. So one common theme with a lot of these atmospheric optical phenomena is that we understand a lot of it, but there's different cases we don't understand. So on this website I'm going through and on the internet, you'll typically find the explanation for sundog. So first, let me describe what a sundog is. Sundog, sometimes they're called perhelia. They're this effect that occurs on top of a 20-degree halo at the very left and the very right edges of the circle. And each dog, as they're called dog for some historical reason. I have no idea why. I forgot to look into it. I never can see why, but I'm sure there's a reason. They're red colored closer to the sun, and sometimes as you move outwards, they can become all the other, similar theme. They always break off into their different colors of the visible spectrum. And they can be really, really bright, like blindingly bright sometimes, depending on the conditions. Other times, they're just these small smudges in the sky. So they have a lot of variability. And like you said, they occur when they're colder. But you tend to see them up north more, and that's because they can also occur from ice crystals that are closer to the Earth. Although a lot of the time they occur way up in the sky in these cirrus, due to these cirrus clouds. So up north, you tend to see more of them due to these ice crystals being closer to the Earth. But yeah, so I was led to believe that they form from what essentially happens is you get these hexagonal ice crystals, but instead of being columns, they're like kind of little pancakes. And as they float downwards, they kind of flatten off roughly, and they reflect and they refract light similar to how the 22-degree halo does, which is why they form on top of the 22-degree halo. They have this hexagonal kind of shape, but because they're kind of flat floating down, they cause the sundogs to be on the very left and the very right edges. But I wouldn't be surprised if recent research shows that it's actually a different effect. So that's something I'm actually going to look into, and maybe I'll come back to it in another episode as an intro topic. But yeah, it's really cool that that's a thing. And there's a lot of these. There's even types of rainbows out there that exist that we don't even have a perfect explanation for yet. Or there's other types of halos. Like I've talked about 2 kind of ice halo effects. There's a huge list of them. And a lot of them form like on this 22-degree halo, which I think is really cool. And it all comes down to these kind of symmetry things that occur with ice crystals in the atmosphere. But yeah, that's interesting. I'm going to look into that.
Yeah, there is this thing with nature and symmetry, isn't it? That a lot of nice phenomena, or even any phenomena, has some form of symmetry to it. If you remember, like particle physics, there's just a bunch of symmetry, SU5, right? U1, U2 plus something, super unitary, blah, 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 the physics stuff. But all these symmetric groups, as we know it, that create a lot of these phenomena.
Yeah, and that's something I want to do an episode on at some point, is symmetry, although it won't be for a while probably, because I don't understand it a lot. But I'm in this QED class right now, this quantum electrodynamics class, and we're talking a lot about kind of group theory and symmetry, and how these symmetries allow for the existence of bosons and fermions and things like that. I'm a little behind in the class, so I have to, read up. But maybe when I'm done with this class, we'll do a symmetry episode. And Patrick, you probably know more about it than I do for sure, because you did particle physics. There's all these this SO2 symmetry, or these all these different things that have to do with a branch of mathematics called group theory.
Yes, certainly bringing up some memories. So we'll have to have a discussion about it at some point.
But that's all I wanted to talk about today. It's not all I wanted to. I want to talk about much more things in more detail, but for the sake of not boring everyone to death with rainbows and shiny things, I think we should move on.
So the take-home message from the rainbows is so the question I asked you before: were there leprechauns, and do rainbows reach the ground?
Depends where you're standing. There's no leprechauns, but if you're it depends where you're standing, because rainbows are this kind of illusion. It's not like light is being emitted from the clouds and it's hitting you. It's bouncing off of raindrops from the sun. So depending where you stand, you're going to see something different. It's kind of like a mirror, right? Like when you look at a mirror, you're not seeing an object through the wall. You're seeing the reflection of something, and where you stand is going to change that. So no leprechauns. And maybe you can see the rainbow touch the ground, but you're going to need raindrops touching the ground, or like continuously being very close to the ground, and you might have to change where you're standing to see it.
So you're saying if you try to catch the end of a rainbow, as we move, the destination is gonna keep changing.
Yeah, and it also will depend on the clouds, right? Like, are they moving? Is the rain getting stronger or weaker? If you chase a rainbow, you may very well walk out of the range that you can see at that angle that I talked about earlier, that the light's kind of sent down to the ground. If you leave that kind of region, the rainbow could disappear.
All right. I think that's pretty good. That's a nice crux or take-home message. And in the spirit of time, we're going to move on to the story. And before that, Patrick is going to tell you how to contact us and how to reach us.
Okay, so if you have any questions about this episode or previous episodes, or just questions in general about any of the topics we've discussed, you can reach out to us through a couple different methods. We can be found on Gmail, and you can email us using the email address hyperthesispodcast@gmail.com. You can also find us on Instagram. We are at the Hyperthesis, where we post updates, so you'll know right when we post an episode. We also have some behind the scenes things, and you can message us on Instagram as well. If you're listening to this, obviously you found us, but we are available on Apple Podcast, Google Podcast, Amazon Music, Spotify. We are based out of Anchor.fm, but we are found on pretty much wherever you get your podcasts. We also do have some exciting news in that we are now on YouTube. So if you want to listen to us on YouTube or watch some very cool rendered videos, it's nothing too spectacular, but it does look very cool with our logo and image, and you get to see the sound waves move, so it's very almost hypnotizing. So go check us out on YouTube. Feel free to subscribe to that and leave us a comment or a review on whatever podcasting service that you use. So the story today, as Liam mentioned earlier, will be about the Northern Lights. So these aren't quite rainbows, but they certainly produce some very beautiful colors in the sky. And we're very fortunate in Canada that we are able to witness this quite often. I don't know about people living in kind of the southern portions of Canada, but as someone who lives at the 53-degree latitude level, I get to see them quite frequently. And I also saw them a lot growing up. Now, Northern Lights, or the Aurora Borealis, there are also Southern Lights, which we won't get into. I believe they're called the Aurora Australis. These lights have lived throughout history in many stories for people who are native to the north. So whether you're from Scandinavia, from Canada, from Russia, there are stories within your history that describe the Northern Lights, whether it's gods reaching down to earth or spirits in the sky. Northern Lights are really quite mystical, but the story I'm going to tell you today is the Northern Lights as told by science and how they are created and these wonderful, spectacular colors just come to be in our sky. And I will focus on the Northern Lights since we are based out of Canada and I've yet to see any Southern Lights. But to begin our story, we have to start in the sun. So the sun, as you know, is a very bright, hot ball of gas that's dense in the center, but not as dense on the outside. And if you've seen videos of it, it's this massive roiling mass of hot, dense gas or plasma. Now, this plasma that's produced, so these ions of positive and negative particles, are constantly being thrown out in what's known as the solar wind. And this solar wind is pretty constant, and it actually shapes the magnetic field of the Earth, which we'll get into in a bit. But there's this constant wind coming from the Earth. But sometimes the magnetic field of the sun, it gets really weird since there's a whole bunch of moving ions everywhere, that what's known as a coronal mass ejection will occur. And now this coronal mass ejection, think just this giant ball of hot plasma that's pushed out of the sun. It's a very hot, very fast-moving ball of this ionized gas or plasma. Now, this coronal mass ejection can eject from the sun anywhere between speeds of 20 kilometers per second to 3,200 kilometers per second, which is quite quickly for particles to move. And this is many, many billions of tons of particles being ejected from the sun at one time. Now, these particles have an average speed of about 500 kilometers per second, which means that if the coronal mass ejection is just in the right place in the sun and it's pointed towards the Earth, it can get to the Earth in 3.5 days. Now, just for reference, light from the sun takes Earth about 8.5 minutes to reach us. So it's slower than that, but definitely faster than most things that we deal with on Earth. Now, as these particles, this roiling mass is moving towards the Earth and gets closer and closer, it begins to interact with the magnetic field of the Earth. Now, Earth's magnetic field is produced by its molten iron core that spins, since the Earth is also spinning. And there's a lot of complicated physics that go on with the Earth's core and how the magnetic field is produced. But because of the molten core, we do have a magnetic field. And as I mentioned earlier, this magnetic field helps protect us against the solar wind and all these very high energy particles that are always being emitted by the sun from reaching the Earth for the most part. So it's essentially like a protective force field around the Earth that keeps dangerous ionizing radiation and harmful particles from reaching us. However, with something like a coronal mass ejection, which is, again, this massive ball of plasma that's speeding towards the Earth, the magnetic field can only do so much. So as these particles start interacting with the magnetic field, there are a couple things that happen. First is that they start to spin. Since they're charged particles, they have an electric field, and moving electric fields will interact with magnetic fields because they're two sides of the same force, the electromagnetic force. And these particles will start to essentially spin along these magnetic field lines. And this spinning almost looks like a corkscrew if you were to draw it out. Now, for very low amounts of ions that are interacting with the magnetic field, the magnetic field is shaped in such a way that it will just spin and then go further off into space. So it wouldn't really interact with Earth. But when you have many, many of these particles interacting with the Earth's magnetic field, then they start generating their own magnetic field. And this magnetic field becomes significant enough that it actually alters the magnetic field of the Earth. Now, this is a very complicated process, which we may have an opportunity to get into someday, especially if we get a space physicist on here. But what happens is what's known as a snapping, where these ions traveling along the lines of the electromagnetic field of Earth cause such a significant change within the field that it snaps, and these particles now have a direct path to Earth. So this snapping also accelerates the particles, meaning that they go towards the source of the electromagnetic field, which is both the northern and southern pole of the Earth. Now, just imagine a very, very fast-moving, corkscrewing particle careening towards Earth. It's running into zero resistance since there's no atmosphere that far out. And then suddenly, there's a whole bunch of molecules and particles that make up the atmosphere. And this isn't good for the particle that's traveling so fast towards the Earth, and it will eventually collide with either an oxygen or a nitrogen. And as we discussed earlier, there's a whole bunch of different types of molecules and gases that make up the atmosphere. And when this particle that originated from the sun eventually collides with a gas in the atmosphere, we get the northern lights, because this particle will come in at such a high speed, it will collide with a gas molecule that will excite the gas molecule, and when that gas molecule then relaxes again, it releases light at a different wavelength depending on the gas. Now, this is happening so often because there's so many particles that originate from the sun that are now interacting with the atmosphere that it starts to produce a very obvious glow. And that glow is the northern lights, or the southern lights. Now, the glow can happen anywhere from 100 kilometers to 600 kilometers above the Earth. There is still gas above the Earth that over 600 kilometers away. It's very not dense, but it can still happen. Now, there are different molecules and different gases in the atmosphere that are responsible for different colors. For those that have seen the northern lights, you may have seen green northern lights, which are the most common. And that's caused by these particles interacting between 100 and 300 kilometers above the surface of the Earth, and they're interacting with oxygen. So it's their powerful collisions with oxygen that cause this green light. However, if you've been lucky, or if it's been dark enough, you can see pink and dark red occasionally. Now, this is where these particles are colliding with nitrogen molecules, and it happens quite low down, around 100 kilometers. So if you were to take the height that you're flying in a plane and multiply that by 10, that's how close the aurora borealis is when you see red. Now, there's also red that's caused a bit higher, which is also collisions with oxygen atoms, but these have different energies in them. And this is a lower energy collision since it's producing red, which, as we discussed earlier, has a lower energy than the green light that's usually produced. Finally, we get to blues and purples. Now, there are hydrogen and helium molecules that are found quite high in the atmosphere because they are less dense than the average atmosphere, and these are very difficult to detect with your eyes. It is possible to see these blues and purples, but I have yet to see them. I don't know about you guys, but they're something that's very rare and very special to see. So all these interactions take place over the course of, could be minutes to hours, but it all started with these particles leaving the sun, traveling all the way and then colliding with the Earth's force field before slipping through, meeting the atmosphere. And the light that's produced from that collision meets our eyes into a very beautiful dance within the atmosphere. So that is the story of how the Northern Lights are produced.
Thank you, Patrick, for an enlightening story. I have actually never seen the Northern Lights. I've never been that far up before, so that's interesting.
On my way to Iceland for a connecting flight to the UK, I saw them for the first time through the plane window over Newfoundland. But what's interesting is that they're in the Canadian Annual Physics Conference in 2022. Me and Feely were there, and there was someone giving a talk. I forget who now, unfortunately, but about like different kinds of northern lights and how there's some different ones we still don't really understand today. And I don't remember the details, but they occur a slightly different way than the typical ones do. So it's interesting that there's all these optical phenomena that occur, and some of them we still don't even understand today.
I will just say one of those is called Steve. It's an acronym now, but it was actually discovered by amateur astronomers and aurora watchers in Alberta, and then later described by someone from the University of Calgary. But Steve is still being studied. We're still not quite sure what causes it, but it's now an acronym, but they just called it Steve. One other thing I will say is that we are in a period of high solar activity, so the chances of seeing northern lights further south is increased. And with large coronal mass injections, you can see them as far as like the southern United States sometimes.
The guy giving that presentation on Steve, he said he wasn't 100% sure. He had no proof, but he was told that the reason why it was called Steve is because these kind of civilian astronomers or these amateur astronomers were at a pub later and they were trying to decide what they should call it. And I think one of them had watched a movie called Over the Hedge or something, and they're like, let's call it Steve after a character in that named Steve. I don't know if that's true, but that's what he said. And then they forcibly gave it an acronym later to say, okay, we want to keep it called Steve, so let's come up with an acronym for it. Anyway, that's funny.
So the hedge was called Steve because it just appeared overnight, and so that was Steve is a very like thin, very long line that appears traveling east to west or west to east in the sky, and so it kind of looks like a hedge, which is part of the reason for the name.
All right, that's very good. But for the interest of time, we're gonna stop it here, and I'll talk to you guys next week. And thank you for listening. Take care.
Bye, everyone.
See ya.